Okay, time for the second basis statistics lecture. We've done t-tests. We started talking about ANOVA. We're going to finish up ANOVA and talk about regression analysis. So we're looking in this space to think about the kind of analysis we're going to do. So today we're going to talk about when we have a categorical independent variable, so a nominal variable, a discrete or categorical variable, and we have a continuous variable as our dependent variable. So, average temperature of forest plots annually by forest type. Is there a difference between boreal forest and temperate forest with respect to the average temperature throughout the year? That would be a question that you could analyze using ANOVA. Okay, so two-factor or two-way ANOVA. So we're going to look at the influence of the levels of two or more factors on a dependent continuous variable. A Model 1 ANOVA is for fixed factor effects. So that means that the levels that you're using of your factor are not randomly selected. You're either testing all of them or a logical subset of the particular factors. And you obtain an estimate of the effect for each level. A Model 2 ANOVA involves random factor effects. So these factor levels are randomly selected or have been assigned using some maybe some knowledge. Maybe you might have a low, medium, and high of something, and you have decided that this is what these levels would be based on previous information, but it's not like species where there's a bright line separating the factor levels. You often have many possible levels, and you select a random sample of those levels. So this does not give you an effect estimate, only an estimation of the variability explained by that particular factor. A Model 3 ANOVA is mixed factor effects, and we're going to leave that aside for now. So Model 1 ANOVA, fixed effects. We have a dependent or response variable there at the left, y of ijk, where I is an observation of one level of factor A, yij, j referring to the level of factor B, and k, the observation. That is, we have, say, 5 observations at factor level A0 and B0, so k would go from 1 to 5. We have an overall mean. We have the factor or the effect of factor A, which is fixed. We have the effect of factor B, also fixed. And then we have a term to represent the interaction between A and B. Then we have the unexplained variation that is going to be left over after we have calculated our factor levels and interactions. So here's an example of two-factor study. We have the effect of endocrine disruptors on salamander growth. And we have the chemical, factor A, that's fixed, either yes or no. We have factor B, male or female, which we'll treat as fixed. And we're going to look at whether or not differences in growth in millimeters per year were different among and between the two factors, exposure to chemical and sex. Our hypothesis is the endocrine disruptor chemical has a negative influence on salamander growth. That's the scientific hypothesis. The statistical hypothesis, the null hypothesis, is that there's no difference in the mean growth rate of salamanders. Now we have multiple hypotheses here. So H sub 0, that's no chemical effect on mean growth rate. HA would be the effect of the factor A, that there is an effect of the disruptor chemical on mean growth rate. And then our second hypothesis will be that there's no gender effect on the mean growth rate, that there is a gender effect on mean growth rate is the hypothesis that we'll be testing. And then the third hypothesis will be that no interaction effect exists on mean growth rate. And of course, then what you're testing is whether there's an interaction effect on mean growth rate. So let's look at the data across factors. So you can see that for both, for all four combinations of the factors, male versus female, contaminant versus no contaminant, we have 5 observations. We can see the sum and then the average for those observations. And immediately what you can see is that it appears as if the existence of the contaminant has, just in absolute terms, reduced the growth rate. So we have like 14.88 and 12.12 millimeters per year growth rate for contaminated salamanders, and 32.52 and 27.78 millimeters per year growth rate for non-contaminated salamanders. So you eyeball it, you can't help yourself. You think maybe there's an effect. Then you would look at, well, in both cases, the males, whether they have contaminant or not, are smaller or have lower growth rates than the females. But immediately below that, what we see is that there's high variance in those growth rates. And so, especially females, non-contaminated, that is a very large number, 69, you have a variance of 69.7 some odd versus an average of 32. So you're thinking, well, okay, well, that's a lot. So just going into it, you might have some feelings about which way it would go, but you also, me looking at this, I say there's a lot of variance, so who can tell? So what are we going to do? We're going to calculate our ANOVA table, okay, and calculate an F value. How are we doing that? Well, this is just showing you that there's a significant effect, apparently, because you see we have the degrees of freedom in the first line. Each one of our variables has a degree of freedom of 1. We have our sum of squares, we have our mean square, and then we've calculated their ratio so that we get, or we've calculated the ratio of the mean square to the within error mean square. So we've gotten a value of 60 for our first F statistic, and that is much larger than the F critical value we're given. So that looks like a significant chemical effect. What does that all mean again? I'll review. Remember, we're looking at the sum of squares total as the sum of squares among plus the sum of squares within. Sum of squares among is just equal to the overall, the effect mean minus the overall mean squared times the number of observations. So we're looking at variation among the various groups. The sum of squares within, in that case, we're looking in the groups, and we're looking at the variance calculated using a single observation and its group mean or level mean, right? So we've got two levels, A or I, which is 1 through the number of levels, J, 1 through the number of observations, Y, I, J, that's an individual observation, minus the average of each level's Y sub I bar average squared. So we're calculating those. And then we're going to calculate this F ratio, the ratio between the mean square, that is the sum of squares divided by the requisite degrees of freedom, in this case, A minus 1, that is levels minus 1, and the sum of mean square within. Sum of squares within divided by n, the number of observations, minus the number of levels. And that gives us our F ratio. That's where we get that number, and you can see that that's basically the 1386.113 divided by 22.89825 to give us 60, okay? And so that gives us our F value, our F critical value. We're going to get from a table, or more likely your computer's going to look it up for you. Again, looking up that F ratio based on the number of degrees of freedom for your among and your degrees of freedom within. Up, you get a value. It's 4.49. And that represents the probability that you would have gotten that F or higher if there were actually no differences among the levels. So we can reject this hypothesis with a fairly good confidence, given that we have a much higher F value than F critical. We're like 60.5, and we only needed to make 4.49. And you can see that with the p-value. That p-value there is whatever it is. It's 7.9 times 10 to the minus 7. So much smaller than the 0.05 we would usually ask for. Now, what about this value? F value for sex. Well, it's about 3, and it does not pass the criteria for the F critical value. So there's a non-significant gender effect and a non-significant interaction effect. You'll see this kind of table for the rest of your life. We'll see very similar tables coming up for regression analysis, okay? So important that you be able to understand it and have a sense for the strength of an effect and what each one of these terms means. Here's a graphical examination of what the effect is. You know, we have on the x-axis, we're looking at just, is the chemical present or isn't it? And then on the y-axis, we have salamander growth rate. We've just plotted some means. And what we found is that there is an effect for A, that is the presence of the chemical, but no effect for B, which is sex. A difference in a significant interaction would be shown by a difference in slopes. And optically, you can kind of look at this. You don't see a difference in slopes. We know that that term is not significant, so no reason to consider it, but that's how it would show up if, in fact, it was significant. Okay, so ANOVA. Now, we're going to go on to looking at regression analysis. Again, independent continuous variable, continuous independent variable, continuous dependent variable. So this is very, very common analysis type. You really need to know how to do this if you're going to be in any kind of scientific setting. And even if you're not, just to understand linear regressions that you may be presented with as a demonstration of the ability to measure something. I work in remote sensing, obviously, so we're always quote unquote measuring or estimating things from, say, a plane. Like we might measure topography during the dry season and topography during the snow season, and subtract one from the other and get the snowpack height. And you'd like to have measurements in the field to tell you, well, does that difference in snowpack height that you estimated using remote sensing correspond with the difference that one would observe with remote sensing and in the field? Or you might say, I am going to use such and such measurement as a proxy for another measurement. So you might measure lizard length and use that as a proxy for lizard weight. And so you might go out and grab a bunch of lizards and, weigh them and measure their length, and then determine if you could estimate one from the other. That would be a linear regression problem. We're analyzing the relationship between two or more continuous variables. Generally, we use regression to look for evidence that changes in one variable are related to, not necessarily cause. Correlation, as I hope you've heard, is not causation. Just because one variable rises when another variable rises, right, doesn't mean that there's a cause there. Could be just that they're both influenced by a third factor. So, is change of one variable related to change in another variable? The predictor or independent variable is almost always X, and the response or dependent variable is almost always Y. Again, a significant relationship between X and Y does not prove a cause and effect relationship, but if you have good study design, you can kind of constrain the possible influences on X and Y that would give you a false correlation. And of course, knowing what you're studying helps. So, how do we write an equation for linear regression? Well, we can have multiple linear regression. That is, we can have multiple independent variables, okay, and where we're trying to predict a single dependent variable. So in that case, it's like we're estimating at the top line y given x using a series of coefficients, betas, b0, b1, b2, etc., and a series of variables, x1, x2, x3, etc., plus some error term. Simplifying this for linear or one univariate regression, we can just say that y is b0 or b0, the intercept of a line, plus beta 1 or beta times x1, coefficient 1 times the independent variable, plus some error. What we're going to do is we're going to use a least squares criteria to minimize the sum of squares between the observed values and the model predicted variables. This is known as ordinary least squares regression, and what it does is the mathematics of it finds the solution for the betas at which the sum of squares, the difference between observed values and model predicted values, where model predicted values are just equal to beta naught plus beta 1 times x1, you're going to reduce the sum of squares. That's what the mathematics does for you. That's not the only way to do it, by the way. There are some times where ordinary least squares regression is not your first choice, but in this case, this is what we're going to talk about. That's what I just said. So, assumptions. That there is a linear relationship between x and y. Okay, that makes sense. Both the response variable and the error term have a Gaussian normal distribution. That for any given value of x, the y values are independent of each other in your data set, and that error term is going to be approximately normal with a mean of 0 and a variance of whatever variance you get. We assume homoscedasticity. That is that the variance of the errors is constant across all the values of x. So in the example that's being shown in the upper right, that looks like a case where you can make that assumption. In cases where you do not have homoscedasticity, what you will see is that, in general, you'll see that the variability of the point appears to increase as a function of the x-axis. That is, they kind of, they say kind of, it gets wider as you go up in values toward the right. I guess there are cases where it's wider near the origin and narrower near the higher values, but I don't think I've ever seen that. So, but it could be either. And the error terms are going to be independent. That is, the residuals are not correlated with anything else. So here's a case where they looked at the effects of fire frequency, and this was measured as the years since a burn, on amphibian species richness. Species richness, again, just the number of species usually. Two hypotheses. One of them is the very popular intermediate disturbance hypothesis. That means, or that suggests that if you have fire very frequently or very infrequently, you will have low species diversity. Very frequently because, maybe the fires are driving out these species and they're not recolonizing. Very infrequently, maybe fires are occurring over such a long time period that the effects of competition are driving out certain species. And that at this intermediate rate of disturbance, we're going to have our highest values for species richness. It's like, what's that story? Goldilocks and Three Bears. It's like too hot, too cold, just right. The second hypothesis is that species richness will continue to increase over larger timescales since a burn. So maybe the effects of migration into your study area over time is just much more important than the effects of competition. So, you just wound up with more and more species as more species are able to find their way back into a particular burned patch. So, that's what you would expect for an intermediate disturbance hypothesis. X-axis, years since last burn. Y-axis, amphibian species richness, and at somewhere between, what is that there? My eyes are failing me, folks. 2 and 4 years. That's, if you have a fire every every 3 years, that's when you're going to get the most richness. Excuse me. Yeah, maybe there's a linear relationship there. Okay, and this is actual data of years since last burn and species richness, and seems like there's a lot of variability, but on the other hand, there also seems to be a nice trend of increasing species richness with the number of years since last burn. So what would the data look like for this? Well, in this case, we would have our unit of analysis is a single pond. So we have 15 ponds here. We have for each pond the years since last burned. Now, it may not seem sensible that you have burned ponds, but in fact, boy, that Cameron Peak fire, if you've been up there, you'll see it did a heck of a job to the local local stream environment. So, you could certainly get burning within some areas, even if they're defined as ponds. And then you go out and you count the number of amphibian species out there. So paired observations from each sampling unit, the pond. And so X will be our years since last burned. Y will be the number of amphibian species. So let's just start with the equation for a line. Y, number of species, is going to be able to equal to some intercept plus beta 1, a slope, times X, the number of the years since burn. Okay. So y-intercept, that's the value of the number of species when there's been no years since a fire. And B1 is going to be the slope of that line, the change in the response for each unit change in the X variable. And then we got to put on the error term to make it a regression model. Because we're not going to explain all the variance in this data set. We've seen the graph. There's obviously a lot of variability in the number of species as a function just of age since burn. You fit the linear model. So we start with a line that just kind of runs through. You could imagine it just being sort of like horizontal through the data, okay? And you then calculate the sum of squares for just that null hypothesis of no response, just a horizontal line. And that's actually going to be the sum of squares of the amphibious species richness. Now, as we rotate the line conceptually, the math is doing this work for us. The differences between each observation and the line are going to change. And because we do seem to have a linear relationship here, as we rotate it up on that right-hand side, the differences between observations D13, D14, and D15 and their predictions based on the equation of the line are going to change, and as it goes up toward approximately the slope that we see there, they're going to become smaller. We have better fit the data than just the null hypothesis of there being no relationship between years since burned and amphibian species richness. And the sum of the squared differences, again, between each one of those observations and the prediction, which is graphically represented by that line, that's going to be your residual sum of squares, okay? Okay, so rotating it, again, conceptually, we've estimated the slope. We've come up with a minimum sum of squares for the possible values of rotating it. And since we know the points on the line, just given 1 point, we can estimate the intercept, right? So if the mean y value, or mean number of species, is equal to beta 0 plus beta 1 times the mean x, then beta 0 must be equal to the mean y minus beta 1 times the mean, beta 0 must be equal to y, the mean y minus beta 1 times the mean x. And that gives us we've gotten our slope and we've gotten our intercept. You, of course, don't do this. The technique used when you're doing least squares regression does this for you. So now the question is, how well does our line do? How well does it predict values of y given x? So in these two cases, we can have the same slope and the same intercept, but very different predictive ability. Clearly, if the relationship on the left is what we found, then we have pretty good confidence. I mean, just, we don't have units there, but everything else being the same between the left and the right-hand graph, you got to think, wow, I have a lot more confidence of that on the left. So how are we going to measure that error? Well, we're going to look at the residuals between the prediction, the line, and the observations. And what we're going to calculate is the residual sum of squares. So we're going to calculate the residual value for each observation. That is the observation minus the prediction given the beta 0 and the beta 1 that we had. Okay, that's the residual sum of squares. And we're going to divide that by n minus 2. And that's going to give us a variance. Okay, scatter around the regression line. So now that we have that, we can test our hypotheses. So null hypothesis, beta 1, the slope, is 0. There's no relationship between x and y. In this case, beta 0 becomes your only estimate of how many species are there. You just know, well, on average, ponds like this, they got 5 species. So all we could say is that there are 5 species on average with some confidence interval. If we come up with a good regression, we can say, oh, well, this particular kind of pond actually has not been burned in quite a while, so it probably has more species. So our null hypothesis is that there's no relationship between x and y, and that changes in y are not associated with changes in x. The hypothesis we're interested in is that beta 1 is not equal to 0, okay? That there is a linear relationship between your x and y, and so your knowledge of x gives you some information about your y value, okay? Alternatively, you could have a one-tailed test. Specifically if you were like, if you were interested, in the hypothesis testing, but weren't interested in making predictions, that's where you might want to use a one-tailed test. But really, I've never seen it. Okay. A reminder, these are estimates of beta 0 and beta 1 because we're working with a sample. We don't have the population. We don't have all the ponds. Our test statistic, again, is going to be the F ratio. So we define that as the mean square among groups versus the mean square within groups. And again, calculations. Well, in this case, we're going to look at the among group as the the mean square explained by the regression. How much variability is being explained by the regression over the mean square of the residual. So the mean square of the residual here is what's left over, obviously. So what's left over is that that residual sum of squares over your number of observations. So the regression or model mean square over the residual or error mean square. So we're back to the data. And we can do these calculations, knowing what our slope and our intercept are, beta 0, beta 1, and we can calculate this, okay? So for this, we have a single degree of freedom associated with the regression, okay? And a mean square of 29.5, okay? And a residual mean square of 6.2. Their ratio is 4.8, and if you looked it up in the table, what you would find is the associated, well, you would get a critical value that's less than 4.8. So your p-value would also be less than 0.05, which means we have a statistically significant p-value. And there at the bottom, we have our coefficients, the betas, intercept 7.1 species plus 0.33 species per year since burn. And then each one of those has a standard error associated with it. And that allows you to understand the confidence with which you know those coefficients, okay? So our standard error is 0.9, and we have p-values associated with each of them, okay? So the intercept, statistically significant, that's, I think, always the case. And then the years since last burned, we also have statistically significant p-value, the same as we have for the overall regression, okay? And then using those standard errors, we can then calculate what are the lower 95th percent and upper 95th percentile values are for the intercept and for the years since last burn. And sometimes you're actually interested in being able to say that, you know, the slope is less than or greater than a certain amount. And those confidence intervals for the coefficients allows you to make statements of that nature. And here you go. There's the sum of square of the regression, residual sum of squares that we've been talking about, and the total sum of squares for all of the observations. Value less than 0.5, just barely. We would use the same technique, I mean, well, if we were doing this, which we're not because the software is, to calculate an F ratio, find the critical value in the table, which in this case is 4.67, and our F critical value is greater, therefore we could reject the null hypothesis that there is no relationship between your X and your Y variable, as shown here. And again, you have your coefficients and the standard errors, etc. So the linear relationship is supported, and the data suggest a beta 1 greater than 0. There's a positive relationship between the number of years since the last burn up to 12 years, and for this particular sample. So I guess one way to say it is that the number of species of the pond increases by 0.33 each year, or You could also say about every 3 years, a new species is added to the pond, which is kind of a lovely thought, actually, especially if you have recently been up to see the damage that was done by the recent fires. So on that note, I'll leave you.